All right, hello and welcome. Today we are going to do something super useful. We're going to dive headfirst into a real GCSE Physics exam paper. I'm going to show you exactly how to take one of those long, tricky questions and turn it into a bunch of easy, straightforward marks.
I mean, this is the question, isn't it? You open the paper, you see this massive question with diagrams, tables, the whole shebang, and it can feel, well, a bit much. But trust me, there's a secret, a method to the madness. It's all about how you take it apart.
And that's the absolute key. You just break it down. We're going to tackle this thing piece by piece, starting right at the beginning. We'll figure out what they're really asking and how to scoop up every last mark.
Okay, so first up, we've got a nice, simple one-mark question. They often kick things off with these, kind of like a warm-up. This one's all about the basics of infrared waves.
And boom, there it is. That's your full mark answer for 01.1. The magic word, the one that gets you the point, is perpendicular. Basically, the wiggles are at a right angle to the direction the wave's moving. Simple as that. 1 mark in the bag.
All right, let's keep the momentum going. The next bit, 01.2, is a big one. We're talking a 6-marker, and it's asking for a whole experimental method. For these, having a super clear logical structure is everything.
So, this is what the student thinks is going to happen. Our job? Design a fair test to check if they're right. So, put your scientist hat on. What are we going to measure? What do we need to keep the same to make it fair? And how do we figure out the answer at the end?
Okay, so listen up. Here is exactly how you nail all 6 of those marks. First, the setup. You fill both flasks with the exact same volume of hot water. Simple enough. Next, you gotta measure. Pop a thermometer in each one and write down that starting temperature. Then, it's all about timing. Start a stopwatch, and for the next 10 minutes, you're gonna record the temperature in each flask, say, every minute. Now this next part, step 4, this is absolutely crucial for the top marks. We're talking control variables. To make sure it's a fair test, you have to keep a bunch of things the same. The flasks need to be the same size and material, and you must have the same starting water temp and volume. Got it? Good. And finally, the conclusion. You just look at your results. The flask that had the biggest drop in temperature, that's the one that emitted more infrared radiation. That's a perfect, beautifully structured answer.
Excellent. Okay, part 3. This one wants us to think a little deeper. When is the rate of this infrared emission at its absolute highest? It's a 2-mark question, so they'll want an answer and a reason why. So, the correct answer for 01.3 is right at the very beginning, during that first minute of cooling. But you know they're going to ask why, and that's exactly where that 2nd mark is hiding.
And here's the beautiful physics behind it. The rate of cooling is always fastest when there's the biggest difference in temperature between the object and its surroundings. So that hot water in the flask compared to the cool air in the room, that difference is at its absolute biggest right at the start. That's your reason.
Okay, get ready for a little switch up. The question is changing gears on us. We've done emission, now we're going to investigate absorption, using these hollow metal cubes you see here. It's a brand new experiment, but you'll see the same scientific thinking applies.
So, question 01.4 asks what the dependent variable is. Quick reminder, that's just the sciencey way of saying the thing you measure to see what happened. So, in this setup, what are we measuring? It's the temperature increase of the water. That's our result.
All right, here's the data they collected, all laid out for us in Table 1. Now, before we even think about the answer, just look at the numbers for a second. Can you see a pattern? You can definitely see some clear differences popping out between the matte and shiny surfaces, right? And between the black and white ones, too. So the exam wants 2 solid conclusions from this table. This means we have to compare the results really carefully to spot 2 different patterns. So what's the story when you compare the matte surfaces to the shiny ones? And what's going on when you look at black versus white? Okay, let's break it down just like the mark scheme would want. Here are the 2 correct conclusions for 01.5. First, have a look at matte black, that's 6.5 degrees, and compare it to shiny black, which is 4.0. Then look at matte white at 3.0 compared to shiny white at 2.0. In both cases, the matte surface got hotter, so conclusion 1 is matte surfaces are better absorbers. Now for the second point. Compare matte black at 6.5 to matte white at 3.0, and shiny black at 4.0 to shiny white at 2.0. The black surfaces always have a bigger temperature increase. So, conclusion 2, black surfaces are better absorbers than white ones. See? 2 clear comparisons, 2 easy marks.
And here we go, the final part of question 1. We're shifting away from experiments now and into pure calculations. Time to get your physics equation sheet handy, although this first one, you should probably know it off by heart.
For question 01.6, it's a spot the right equation kind of deal. And there it is, pressure equals force divided by area. Lock that in, because it's the key to the very last part of this question.
All right, this is it, the grand finale for question 1, a meaty 4-mark calculation. So here's what we know. The pressure at the bottom of this cube is 1,500 pascals. We can also see its sides are 0.12 meters long. Our mission, should we choose to accept it, is to calculate the force.
Let's walk through this step by step, exactly how an examiner wants to see it. First things first, we need the area. That's just length times width. So 0.12 times 0.12, which gives us 0.0144 square meters. Easy. Step 2, we need to rearrange our formula. If pressure is force over area, then force must be pressure times area. Make sense? Okay, step 3, we just plug in the numbers we know. So force is 1,500 pascals times our area of 0.0144 square meters. All that's left is to solve it. And the final answer comes out to 21.6 newtons. And because you showed every single step, calculating the area, rearranging the formula, substituting the values, and getting the final answer, you have just locked in all 4 of those marks. What a brilliant way to finish.
You know, let's just take a breath for a second and look at what we just did. In that one single question, we had to remember a definition, design a whole experiment, look at data and figure out what it means, and do a multi-step calculation. That's a massive range of skills all rolled into one.
And really, that's the big secret, isn't it? A long, scary-looking exam question isn't one giant, impossible monster. It's just a bunch of little, manageable problems all lined up in a row. If you just tackle them one by one, nice and methodically, you can turn something that looks totally daunting into a whole series of wins. The real takeaway? Every big problem is just a series of small ones. So, feeling more confident? Good. Now, what question should we break down next?